Alright, moving on. Let's look at problem number 17. And here we want to find the zero and the x-intercept of the given linear function. So we have a function f of x equal to 7x minus 63, a linear function. We've got our x term, 7x. Again, this is our slope-intercept form, right, for a line, y equal mx plus b form. So we can look at it and see the slope, right, slope being 7, and we can see the y-intercept point. Right, so again, before we begin, let's make note of that. Review a little bit. Our slope is 7. So again, that means we have a increasing line, right? Up 7, right 1, up 7, right 1. We have a y-intercept point. Our y-intercept point is at 0b. So b being negative 63, our constant term. So again, we have slope-intercept form. Now to find the zero, so remember, zeros is any number that can be plugged into your function to make an output of 0. So again, to find a 0 algebraically, we want to know when our function equals 0. So that's our work. So when is f of x equals 0? So let's go do that. So that implies 7x minus 63 needs to equal 0. So setting our function equals 0. And let's go solve it. So now we'll know what x equals. So as we do that, right, as we got to move the constant term over, so we can go ahead and add a 63 over to the other side of the equation. And that gives us an equation that reads 7x equal to 63. And then we can divide out our coefficient. So we can divide out a 7 on both sides. As we do that, we come up with a value of x equaling 9. So that's our 0. So here's our number, our input for x, right? That would give us an output of 0. For example, if you wanted to check, do our check step, right? What would f of 9 equal? It would equal 7 times 9 minus 63, which is 63 minus 63, which equals 0. Now that also leads us to our x-intercept point. So our x-intercept is again the location of the 0. So our x-intercept would be the order pair 9, 0. So again, if you were graphing this function, so if you want to get a quick sketch of this linear function that we've just found, just to see that, right, our y-intercept be down here at 0, negative 63. Our y-intercept point. And we graph in this line here. And let's go ahead and graph it in. And here's our graph. And then our x-intercept, which right here would be the location of that 0. There's the point 9, 0. So you see a graph of this linear function. So here's f of x equal to 7x minus 63. Now with that said, you can check it. So remember, you can also look at zeros on your calculator. Let's review that if you want. So let's get our calculator out. And let's store in this linear function, 7x minus 63. I'm going to store it in here in y1. So hit your y equal button. And we can graph this line. Let's go with standard window. Hit our zoom key at the top. Zoom 6, get a negative 10 to 10. And you can see, of course, the x-intercept point, right? Here's where our 0 is located. Now, as we want to find that, right, out with our grapher, what we're going to have to do, the trace button won't do it. You can guess with trace. But remember the second trace button. Above the word trace at the top, your trace key, it says calc. Remember, second trace, second calc, is where you find your 0 command, your min, your max commands, intersect commands. Different commands we'll be using this semester, but we talked about 0 and intersect back in our section 5 lecture when we were looking at different ways to check equations graphically. But a 0, again, a location x-intercept, can be found by hitting that command. It asks you 2 questions. So you should see probably the bottom left corner of your calculator. Mine is at the top, says left bound. And you can see my cursor over here. It's right now to the right of the 0. The x-intercept location is our 0. So hit your left arrow key and go somewhere below the x-axis, which would be on the left-hand side of the x-intercept, which is the left bound for the 0. Anywhere over here would be left bound. Hit enter, and it marks that bound. I marked mine at 8.878 approximately. You see down at the bottom where you are, your ordered pair. And then I'm going to go above the x-axis to get a right bound. And you see the new question. It says right bound. Make sure you're to the right of the x-intercept, which is where your 0 is. And hit enter, and then enter a third time, and it'll lock in on the 0. You can see down here at the bottom it says 0 at x equal to 9. So again, you got your TI. Again, remember you can check those zeros. So that's a review of zeros, and we talk about zeros when we talk about getting quick points, right, for any type of function. That's an easy, zero is easy to find, right? You just set your function equals 0 and solve it, and you're finding some quick points to graph. You're finding your x-intercept points for your graph, right? So in a linear function, in a slope-intercept form, you see one point, the y-intercept. Now we've taken it and found a way to get another point easily by getting the x-intercept point, which is by finding the 0. Looking at problem 18, let's move on. Let's solve this linear equation. Let's solve for x. You can see our variable x here. We've got our x term on both sides of the equation. We want to know what x equals. Well, our first step, we need to go ahead and distribute. So let's go ahead and distribute. That's going to be our first step, is to apply the distributive property. So as we do that, we got 2 times x, which is 2x, right? And then we have 2 times 6, which is 12, equal to 6 minus distribute, clear out the parentheses, minus 4 times x is minus 4x, minus 4 times 6 is minus 24. So clearing the parentheses, distributing. Again, we want to know what x equals. So again, you see your 2x terms, one on each side of the equation. All right, let's go ahead, while we're at it, let's go ahead and simplify the right-hand side. So we've got a couple of like terms. Let's go ahead and combine those. So 2x plus 12 equals negative 4x minus what, 18? 6 minus 24 equals negative 18. And then what are we going to do next? We're going to move our terms. Let's go ahead and move the x term over to the left side. We'll put them together on the left side. And then we'll move the constant term over to the right side. We're going to isolate. We want to know again what x is equal to. Solve for x. So let's go ahead and do that. So as we subtract our 12 on both sides of the equation, right, and we add our 4x to both sides of the equation, we get an equation that reads 6x equal to what? Negative 18 minus 12, which is negative 30, right? Which, as we solve x, last step, divide out our coefficient, 6 divided by 6, 1, so x is equal to negative 5. So there's our solution to this linear equation, right? And you could check it. I mean, if you wanted to graph it to check it, you could. You can plug it in and substitute the check. Make sure you do take the time and check your work. So again, make sure you take that extra step. Do your check step. This won't take long by hand. But 2 times x, 2 times negative 5 plus 6, right, and we'll check by substitution, equals 6 minus 4 times negative 5 plus 6. So let's see if that simplifies down. So that's 2 times what? This is 1 equal to 6 minus 4 times negative 5 plus 6, which is 1. As we simplify that, we got 2 equal to 6 minus 4, which is also 2. So yeah, 2 equal 2, it checks. So again, that's a quick check step. Now that's checking, of course, algebraically. Check it graphically if you wanted. You could do your intersection command. You could do your 0 command. We talked about that earlier in the chapter, different ways to check your work. Main thing being to solve it algebraically. So that's a review. We should not solve a linear equation, right? Got to get x by itself on one side of the equation. Use your properties. We use the addition property, equality, and multiplication property, equality to finally get down to x. Moving on, let's solve this next equation. Now this is a linear equation. It's an equation, though, that has 3 different variables. We got v, b, and h. So it says to solve for b. So we got three first-degree variables, right? It's a linear equation with multiple variables. But if I want to solve for b, the first thing I'm going to do, right, is go ahead and get rid of the coefficient. So, or get rid of that fraction. I don't like fractions. So let's go ahead and get rid of that. Let's multiply both sides by 3. Right, so again, as we take our equation, let's go ahead and write it down. So again, v is equal to 1/3 times bh. So again, as I see this 3 down here, I'm going to times by 3. So I'm going to multiply both sides by 3. And as I do that, right, we can do anything we want on both sides as long as it's the same, right? We multiply both sides by 3, still equal. Multiplication property of equality. 3v, right, is equal to, well, 1/3 times 3. The 3's divide out, and that simplifies down to bh. And then if we're solving for b, keep in mind, we want to know what b equals. So our last step is to get rid of that coefficient of b. So we're going to divide out h, right, on both sides of the equation. As we do that, we get 3v divided by h equal to b. Well, there it is. There's our solution. So what does b equal? B equals 3v over h. Right? So we're solving that equation for b, writing in terms of v and h. All right, so again, that's taking an equation. That's a formula, right, from geometry. And you're looking back into volume for a cone or pyramid. Your volume is 1/3 of the base, your area base, times your height. All right, so again, that's where that comes from. But looking at 20, let's go to the next page here. Let's get into inequalities. Let's solve a linear inequality. It says write our solution set in interval form. Our preferred form, we have infinite set of answers like we do with inequalities. So let's look at this first one. So as we're solving, we notice we got x as our variable unknown. Well, again, no different than solving a linear equation. You just got to remember that whenever we multiply or divide by negative, you got to flip, right? You got to reverse the inequality symbols. So let's go ahead and get the x terms together. So that would be my first step. Let's go ahead and add a 5x to both sides of the equation. Now again, adding or subtracting a number or a term doesn't change the inequality, and it's multiplying or dividing by negative that does. All right, let's go ahead and do that. Let's go ahead and move the constant term while we're at it. Let's go ahead and move it over to the other side of the equation. So I'll go ahead and subtract 8 on both sides. So rearranging my terms, negative 6x plus 5x is negative x. And again, as we're solving for x, greater than or equal to, and x terms eliminated, we got negative 10. And then as we solve for x, we're going to divide out our coefficient, which our coefficient is negative 1. So we can go ahead and multiply or divide both sides by negative. Now here's where you got to be careful. You must reverse this inequality symbol. So it's now going to be a less than equal to because of the negative. So x must be less than equal to 10. So there's my solution set. Now as we look at that different ways, there's a statement of solutions. What is x less than equal to 10? Let's look at it graphically. Here's all real numbers x. Let's look at our x line. Less than equal to 10 means 10 is a solution. So I'm going to shade in all these values equal to 10 or less than, which leads us to our interval. So what they ask for in the directions is the interval notation. So all numbers less than equal to 10. Right, there's our interval form for that inequality. So again, solving a inequality, right, we've done that. Now let's go ahead and look at a compound inequality. So as you look at problem 21, it's a little different. And 21 is a little different in that we have actually two inequalities being joined up together. This is a 3-part inequality with our unknown or variable z here in the middle. So we got to solve for z. So let's go do that. So we're trying to solve for z, which again, z is in the middle there. Now as we solve that, let's go ahead and isolate. I'm going to go ahead and get rid of the 4. So I'm going to subtract a 4 from all 3 parts. And as I do that, I got a 0. And then here in the middle, I've got a negative 3z. Right? Now, nothing changes with inequality symbols, right? Because, what? I'm not multiplying or dividing by negative. So they stay the same. Now, as we go to our last step, let's divide out our coefficient. That's just a negative 3. It's our last step to get z by itself. Now, as we do that, we must reverse because we're dividing by negative. So anytime we multiply or divide by negative, we must reverse the inequality symbol. So we'll go ahead and do that. So we got to flip those. So notice those are reversed because of the negative, right? Now, as we look at that as a statement of solutions, all right, I'm going to write that right here beside it. That states, this is a 3-part inequality. It's 2 inequalities joined up. This states that z is greater than or equal to negative 4, and at the same time, z must be less than 0. So it's got 2 restrictions on our variable z. So it must be greater than or equal to negative 4, and at the same time less than 0. So if you were taking that and looking at it as a graph of solutions, let's graph in the solution set. Let's draw in our z line. Here's all real number z. And let's place negative 4 and 0 on here. Greater than or equal to negative 4 means negative 4 is an answer. And greater than, usually we go all the way to infinity. Now here's the difference. And means at the same time it must satisfy the other inequality, which says it has to be less than 0. So that means it can't equal 0. So I'll put a little open circle on that. So that you see our solution set is bounded between 2 numbers. That's what happens with our 3-part inequalities, our AND inequalities. Now let's go ahead and write in the interval. So the interval will be a bracket on negative 4, we'll include that, and then a parentheses on 0. So all real numbers greater than or equal to negative 4 and less than 0. There's our solution set, right, for that compound inequality. So again, solving a 3-part inequality, an AND inequality. Let's solve another compound inequality. In problem number 22, we've got 2 inequalities joined together with the word OR. It's a little different than our last one. Last problem we had an AND problem. We got 2 restrictions on the variable. Well, this one is 2 different inequalities. It can satisfy either one to be a solution. It doesn't have to work both at the same time like it does with AND problems. With that said, let's go ahead and solve it. So we're going to solve for x. We've got to isolate x. So the first thing we'll do is get ahead and get rid of the constant term. Let's go ahead and subtract the 1 on both sides. We'll work both of these inequalities at the same time. And as we do that, we get negative 4x greater than or equal to 9. Or over here, we got negative 4x less than 3. And then as we go to our last step to get x isolated, we got to divide out the negative 4 on both sides of the inequality. And remember, when we do that, we must reverse because of the negative. Now, if it's a positive number, it doesn't reverse, doesn't flip, but only with negatives. So this is x less than or equal to negative 9/4, which is negative 2 1/4. Right, you want to write as a mixed number. Or x greater than, we got to flip. So notice we have reversed these inequality symbols, greater than negative 3/4. So as you look at those, let's go ahead and take a graph of these solutions. So let's build in our x line. Here's all real numbers x. So let's graph what we just found there. So negative 9/4, which again, negative, 2 1/4, which would be to the left is less than negative 3/4. So that's over here to the right of it. Now with that said, x less than or equal to negative 9/4 means negative 9/4 is a solution. And I'd shade in all these numbers. Or, and we have solutions greater than, not greater than equal to. So put a little open circle to denote that. But there's a graph of the solution sets. Now as we look at that as an interval goes, right, we're looking at negative infinity to negative 9/4 bracket. And we'll use my union symbol, which is OR in math, or greater than negative 3/4. So there's our statement of solutions in an interval form. Pick a number out of either interval. It's going to work one of those two inequalities. Now, had we had an AND problem, there would not be a solution. There's no common value, right? There's no overlap in these two graphs, no intersection, right? There is no solution if we're looking for something that satisfies both inequalities, but we needed one or the other. So there's infinite solutions that work for one or the other. Now, as we move on, let's go to absolute values to finish off our topics. First one we have is an absolute value equation. So solving that, pretty straightforward. You just got to remember your definition of an absolute value. Now your first step is to isolate the absolute value term. So the first step here would be to add a 4 to both sides so we can get that absolute value term by itself. So as we do that, right, what do we have? Absolute value of x plus 8 equal to 16. And now is where our definition comes in, right? If we're looking at an absolute value, right, so if you take the definition for some number a greater than 0, all right, that implies if the absolute value of x equals some number a, that implies x can be equal to negative a, or x can equal positive a. So definition, right, of absolute value. So I wanted to show that to you, our definition. So let's go ahead and apply that. So we want to know when our absolute value equals 16. So that means inside here, right, we can be either negative 16 or 16, right? One of those two, because the absolute value, remember, is a distance, right? It's a distance that number is from 0. So again, we want to know when we're 16 units from 0. That would be negative 16 or 16. So that implies x plus 8 can equal negative 16, or x plus 8 can equal positive 16. So set up your two equations. There's x equal negative a or x equal positive a definition. And now we'll know what x equals. So again, we applied our definition. So I'll make a little note here on the side, absolute value definition. Apply it. And as we're solving it, let's go ahead and solve for x. Go ahead and move that 8 over, and we'll have our solutions. And as we see here, we get the absolute value. We got x equal negative 24. Over here, we got x equal to 8. So I got two different solutions. And you check them. You plug those in, do your check step. Right, negative 24 plus 8 is negative 16. Absolute value negative 16, 16. 16 minus 4 is 12. Plug in 8, 8 plus 8 is 16, absolute value is 16, 16 minus 4 is 12. So it does check, so you check them, you can graph it and check it. It's also a good way to look at them graphically, right, if you want to check those on your grapher. Let's move on. Looking at our last two problems, 24 and 25, wants us to solve these absolute value inequalities and to state our solutions with an interval. So we're back to inequalities. So we're going to have an infinite set of values as a possibility of solutions. So let's go ahead and see what happens. Now as we solve, no different than we just did the equations. We've got to isolate the absolute value term. That's going to be our first step. So to isolate, let's go ahead and move the 4 over. So we'll subtract 4. That would be my first step. So that gives me 2 times the absolute value of 2x plus 7 equal to, or I shouldn't say equal to, this is an inequality, less than 38, right, as we subtract the 4 over. And then we still got a 2 sitting out in front as a coefficient. So we need to go ahead and divide that 2 out. And as we do that, we finally got the absolute value term isolated. So the absolute value of 2x plus 7 less than 38 divided by 2, which is 19. Well, with that, we now got our definition. So now we're ready to apply the absolute value definition. So we'll make a little note over here on the side. So again, absolute value definition. Let's apply that. So we know, again, with 2x plus 7, we want absolute value to be 19. Right, we're going to be looking at negative 19 or 19. So we got to set up those two inequalities. So let's go ahead and do that. So applying the definition, that implies 2x plus 7. Now, when we use negative 19, right, we have this less than symbol. We must reverse and flip. So that's now going to be a greater than symbol because I'm getting a negative 19. I'm multiplying by negative 1 to make negative 19. I got to flip the inequality symbol. So make sure you reverse it when you use the negative. All right, now with less than problems, all less than problems are and problems. And at the same time, 2x plus 7, we leave it alone, can be less than 19. So there they are. We're setting up those two inequalities. We're setting up a compound inequality. Now as we solve that for x, let's go ahead and solve it. Go ahead and subtract 7. Now adding or subtracting a constant doesn't matter. Positive or negative doesn't change the inequality symbols. All multiply and divide by negative. So as we do that, we got 2x greater than negative 26, negative 19 minus 7. And at the same time, 2x over here is less than 19 minus 7, which is what? 11? I'm sorry, 12. So we subtract 7 from that one. And with that said, right, we're down to our last step, divide out our coefficient. So we'll divide out a 2 on both sides. All right, as we do that, now we're not multiplying and dividing by negative 2, we're dividing by positive. So nothing changes with the inequality symbol. So x is greater than negative 13. And over here we got x less than 6. So you're looking at that as a compound inequality. You want to graph it. Let's show that solution set. So negative 13 and 6. So greater than negative 13, less than 6, all these numbers in between. So remember, that's what happens with these compound and inequalities, right? Which we saw earlier with our three-part inequality, which is what you could have done with this one. Build it as a three-part, bounded between negative 19 and 19. But again, in the end, let's write our interval. So negative 13, comma 6. Now I need parentheses. They're both just less than, greater than, not equal to. But there it is in interval form. So writing our interval notation. Right, there's our solution set in interval form. So again, that's an absolute value inequality that we've solved here. Now let's look at this next one. Let's take 25, and what I'm going to do, I'm going to bring 25 on down. So with problem number 25, we've got the absolute value of 4x minus 1 minus 3 greater than or equal to 3. So first step, again, isolate. So anything attached to your absolute value term, get it by itself. So we have a minus 3 with it, need to add it. Now again, doesn't change anything with the inequality symbol, not multiplying, dividing by negative. Absolute value of 4x minus 1 greater than or equal to 6. So move that over. And then we apply our definition. So now ready for step 2. Again, apply definition of absolute value. So as we do that, we know 4x minus 1. If we want it to be 6, we can have a negative 6 or positive 6. Now, one thing I want to make note of, all greater than problems are or problems. All less than problems are and problems. So as we look at it, we got 4x minus 1. Now I got to reverse it. Less than or equal to. Got to flip it because of the negative. Or, I'll leave it alone, 4x minus 1 greater than or equal to 6. So there it is, our compound inequality. Now this one is a or inequality. Just make sure you flip when you use a negative. Now as we solve that for x, we'll go ahead and get x by itself. Go ahead and add a 1 over on both sides. So we have 4x less than or equal to negative 5. Over here we got 4x greater than or equal to 7. And then our last step, dividing out the 4, the coefficient on both sides. And this is a positive 4, so nothing changes with the inequality symbol. So x less than or equal to negative 5/4, or x greater than or equal to 7/4. And again, if you want to look at it on a graph, makes it easier to see the interval. Let's go ahead and state these two critical values. Less than or equal to, again, shading in those numbers that satisfy that, or greater than or equal to 7/4. Again, infinite solutions. Let's write that in the interval form. So negative infinity, looking at it all the way to negative 5/4. Now we need a bracket. It's important. Less than or equal to, or, so union, bracket 7/4, which is what? 1 3/4. So 7/4 all the way to infinity. There's our statement of solutions in our preferred form, in our interval form. So there's our interval notation. So again, that's a compound inequality after we apply the definition of absolute value, right? We had two inequalities set up. So again, with absolute values, you're going to have to apply your definition of absolute value. So remember our definition, right? Where absolute value is a distance. So we got it equal to some number a. Now that number needs to be a positive number, or it could equal 0. But some positive number, we can be negative or positive and have that same distance from 0. So again, that's where you're getting your two different inequalities set up. But that's their absolute values, and that finishes off our unit review. So I hope that helps you with Unit 1.